Hi students, this Vodcast concerns atomic mass. So what you should understand by now is what atomic number is. You should understand what mass number is, but you should also understand there's another number on the periodic table called the atomic mass. So today we are going to try to understand where that atomic mass comes from. A bit of a review is required. Let's remember that we have isotope symbols for elements. Here's lithium-6 is what we call it. It has a mass number of 6 and an atomic number of 3. A little bit heavier version of lithium is lithium-7. Still has 3 protons, but it has 4 neutrons in its nucleus, which gives it a mass number of 7. So today we're going to talk about the average atomic mass. That's what ends up on the periodic table. And it's not just an average, it's something called a weighted average. So this is usually where students start to struggle a little bit. They say if there are 2 isotopes of lithium, lithium-6 and lithium-7, and I average those 2, then the mass should be 6.5. That's halfway in between. That's my average. But if you look at the element block on the periodic table, the average atomic mass, that's this number down here, is 6.941. So something else must be going on here. And remember, for this unit, you have 2 choices for labs, either the PhET simulation, and I've included that packet in your handout, or there is a lab on page 120 of your book. So those are good labs to do really at any point when you're trying to understand average atomic mass. Let's talk about the calculations that go into finding average atomic mass. You'll take the mass of your first isotope times its percent abundance. Some isotopes just occur more commonly than others, and we call how commonly they occur your percent abundance. Then you're going to add that to this right here. You take the mass of isotope 2 times its percent abundance. And then you take your first number you got, you add it to the second number you got. And that's going to give you your average atomic mass. It is important when you're working with percentages to change that percentage to a decimal. You just move that decimal 2 places to the left, and that will give you your percent abundance in a decimal format. So let's see how this math would look. Down here for carbon, if I have 1 isotope of carbon with a mass number of 12, and another isotope of carbon with a mass number of 13, and here are their atomic weights. Here are their percent abundances. Let's say that 98.9% of carbon in a sample I have is carbon-12, and only 1.10% of the carbon in my sample is carbon-13. Well, you can probably already tell that when I put these 2 together, my average is going to be closer to 12 than it is to 13 because there's so many more carbon-12s in this particular sample. So we've made a prediction that it's going to be close to 12, my average atomic mass is. So I take the mass of isotope 1, my carbon-12, 12.00 atomic mass units, AMUs, that's the unit that we're going to be using, that was created to express the mass of atoms, times its percent abundance. Oops, I made a little mistake here. I put my percent right there in the problem. When you're putting this into your calculator, you should type in 12.00 times 0.9890. Don't hit the percent button then. That'll get you all kinds of weirded out. So that's your first part. Then you take 13 times 0.0110, and again, don't hit the percent button, but it's 0.0110. That's 1.10% changed to a decimal. Okay, so when I take this part here in parentheses and I add it to that part here in parentheses, my answer should be 12.011 AMUs, atomic mass units. So does this answer make sense? Since most of the carbons in my sample, 98.9% of them, have this mass, then that makes sense that the average mass is really close to 12, to the more abundant one. So take a moment, try typing this into your calculator, either on your phone or on the iPad, and make sure that when you type this in, you get here. And if you're struggling with that, let me know. It might just be the order in which you're putting them in. Let's try another one. Here's the information about magnesium. If magnesium has 3 naturally occurring isotopes, there's the information for all of them. And we need to find the average atomic mass of magnesium. You can start to make an estimation. Most of my atoms in this sample, almost 79%, exist as magnesium-24, and there's its mass, 23.9850. So I think my answer is going to end up close to that. Closer than to the other 2 isotopes. Let's give it a try. So I take my atomic mass of my first isotope, 23.9850, and I multiply it by my percent abundance that I've changed to a decimal. 78.70 is 0.7870, and I multiply those two numbers, and there's what I get. I do the same thing for the next two isotopes. There's that one. And I get 2.506, and then my third isotope, I do the same thing. I take the atomic mass of it times its percent abundance. And now once I've gotten all of these, I add them together. And don't forget your units. It's AMU. So 24.29 atomic mass units. Does this answer make sense? Yes, because almost 80% of my magnesium atoms are going to have this mass. It's very close to 24. This mass is close to 24, a little bit higher than 24. That is how you find the average atomic mass. And then I can go look on the periodic table and see if this number that I calculated right here is close to what is on the periodic table. That is how you find average atomic mass. I've given you some homework problems and worksheets on this, and you will be expected to know this for your atomic mass quiz.